in the previous section, we studied exponential growth and exponential increase, that is growth, and exponential decrease, that is exponential decay. So now in this section, we're going to look at specific examples and of exponential growth and decay and other terms related to this sort of a process. In a growth pattern that is exponential, you start off with a certain quantity and it keeps growing exponentially in the exponential pattern. And at some point, it would have to double. Now, how long does it take for a quantity to double itself in the exponential situation? So that would be a specific term, and it's denoted by the doubling time, and that is denoted by T subscript double. So that's the doubling time. That's an important term in exponential growth. Now, you start off with a certain quantity, and as time passes, there is growth. So it changes to a new value. So the initial value is the term used for what you start off with, and the new value is what it becomes after the growth in a certain time period, that is T. So you need to know 4 different terms. One is the new value. You need to know what that means. So when something grows, it changes to a new quantity, and that is your new value. You start off with an initial amount, and that's your initial value. T double, really quickly again, it's the doubling time, and the letter lowercase t is for a specific time in the process. So the first formula that we've come across is this. The new value, I'm just going to call it n, is equal to the initial value I times 2 to the specific time t over the doubling time t double. Now, if I divide both sides by I, so I'd get n over I, so the new value over the initial value. The I is divided by I, so that cancels, and then you go times 2 to the t over t doubling time. So what we have is just a different form of the same formula. The new value over the initial value is 2 to the t over t double. So this quantity gives us the fraction of the initial value that remains, or that is after a certain time period t. If we need to find the fraction of or the factor that the initial value grows by, so that would be given by the new value over initial value equals 2 to the t over t double. So if we're given this formula, then we might have to do the algebra and use this sometimes in certain problems. So looking at the first question, we're talking about exponential growth here. The doubling time of a bank account is 20 years. So that is the doubling time, which is denoted by T double, which is equal to 20 years. By what factor does it grow in 40 years? So if the time T is equal to 40 years, by what factor does it grow? Which means, what is the ratio or the fraction new value over initial value? That is what the question is asking, the factor by which it grows. So basically, it is this formula we were talking about previously. N over I is, this is what we're going to use. N over I is equal to 2 to the t over t double. So new value over initial value is equal to the factor by which it grows in t years. And we know what the formula is. It's 2 to the t, the present time t, that is the time at which we're interested in that information, over t double. Plugging in the numbers, so that's 40 years. By what factor does it grow in 40 years? So that is 40, divided by the doubling time, that's 20. So That gives us 2 squared. 40 over 20 is 2, and that is 4. So the factor by which um, your money grows in that account in 40 years is 4. So if you put $100 today, then in 4 years, you're going to have $400 in this account. Not 4,000, sorry, it's $400. Another similar example of growth, exponential growth. The initial population, so the starting value or the initial value is 10,000. So that's what we have here. So that's the initial population of the town, and it grows with a doubling time of 8 years. So it doubles in 8 years. So every piece of information, just turn it into mathematical notation and then plug it into the right formula and you're done. So the doubling time is 8 years. What will the population be in 12 years, in 24 years? So it doesn't matter what, you just have to plug in the t for each situation. So in 12 years, t is equal to 12. We know the initial value. We know the t double, the doubling time, at a certain time period, 12. So plugging in all the numbers, we get 10,000 times 2 to the 12 over 8, and that gives us the new population based on the doubling time. So that would be 28,284 people. In 24 years, the information is exactly the same as far as initial value is concerned. That's always starting point, which is 10,000. The doubling time is the same thing because we're talking about the same population. We need to figure out the new value at a different period of time. So the only thing different here is t equals 24. So plugging in all the numbers, because we need to figure out the new value. So that would be initial value times 2 to the t over t double. Plugging in all the numbers, we get 80,000 people. Here again, similar situation, exponential growth of 3.5% every year. So that is the exponential growth factor. What is the doubling time is the question. So here we are trying to figure out the doubling time. And then the next question is, by what factor will the population increase in 50 years? So let's answer the first part of the question. Now, the doubling time is related to the percentage growth or decrease, which we're going to see later, by this equation. As long as the growth percent is less than 15, this formula works okay. It's an approximation, but sometimes we don't need exact values. We can do with approximations, and that's what it is. The P here is the percent per period, whether it's a year or a week or a day. So 70 t double, the doubling time is approximately, so this is a symbol for approximately, equal to 70 divided by P, and that would be roughly, or exactly, sorry, 20 years. And it's years, the unit is years because the percentage growth is per year. So now we know the doubling time. Now we need to find the factor by which the population increases in 50 years. Remember, to find the factor, we need to use this version of the formula. New value over initial value is equal to 2 to the t over t double. And now we are familiar with what t double is. It's the doubling time, which we just found out is 20 years. T is the time at which we need to find the growth factor, and here it's 50 years. So new value over initial value is equal to 2 to the 50 over t double, which is 20 years. And that is about 5.66 growth factor. So in 50 years, the population is about 6 times what it started off with. So if it is about 1,000 at the beginning of time, in 50 years, so this is time t equals 0, in 50 years, the population will be about, that is approximately 6 times, since we can approximately say this is 6 times, it is 6 times 1,000, so that is equal to 6,000. So the growth factor is 6 times the initial value. The similar example, we have oil consumption is increasing, so here it's an increase at a rate of 2.2% per year. If it's increasing at the exact same percent every year, it's exponential. What is its doubling time? So we know that we have a formula for doubling time, which is approximately equal to 70 over P. P is the percent. So so it's not really the percent, but just this number, 2.2. Plug it in here. Don't change it to the decimal form by dividing by 100. So 70 over 2.2 is 31.82 years, which is approximately equal to 32 years. So we just plugged it into the formula for doubling time, which is 70, a fixed number, over the percent change, which is an increase every year. So it's 31.82 years, which is approximately about 32 years. That's the doubling time. Now we can figure out the factor. So new value over initial value is equal to 2 to the t over t double. So this is the factor by which the oil consumption increases. So let's plug in the numbers. So N over I is equal to 2 to the t, which is in a decade, let's say that's 10 years, divided by t double, which is about 32 years. So when we simplify this, 2 to the 10 divided by 32, let's use our calculators. We get 2 to the 10 divided by 32, and that is about 1.24. So that would be the factor, the growth factor. It would be 1.24 times the previous, the starting point. Now, just like we have exponential growth, where a quantity is growing exponentially, we could also have exponential decay or decrease. So if a quantity is growing, then at some point it doubles itself. Similarly, when a quantity is decreasing or decaying, at some point it would be half of itself. So that number is important. It is called the half-life of that particular process or substance. So the half-life is denoted by T subscript half. So that is called the half-life. Just like we have the doubling life for exponential growth, we have the half-life for exponential decay. And you can see that this formula looks exactly like the exponential growth, except that instead of 2, we have half to the t divided by t half. Now, if you remember, the new value was equal to the initial value times 2 to the t over t double for exponential growth. Just compare the two, and the only difference you're going to see is t half instead of t double, and half instead of 2, since it is decay. It's going to be half of itself every period. So if we want to find the factor by which it decays, then we use this, or we need to find the new value given the initial value and everything else, we use this formula. Now, just like before, we can calculate the half-life of any substance if we know the percent by which it decreases in periods. And this formula, just like before, it gives you an approximation, not an exact quantity, and it works best when it is a percent decay or decrease, which is smaller than 15%. It shouldn't be greater than 15%.